Hey guys, this is Steven Mossberger from the school group, another school group exclusive for hardware development school.com. In this video, we're going to be talking about the design slash system FMECA and how to fill one out. And we'll jump into the examples to look at some of these different parts. Let's go ahead and talk about it. So this one, I filmed the safety Fumika before this one, so make sure you also check out that explanation as well. This one is a little different because the mitigations are a little bit more creative than the safety Fumika. Safety Fumika generally has some set guidelines of what you can use to do a mitigation. This one has a lot of different mitigations, right? It could be just changing the component, could be a mitigation, right? Or going to a different supplier, different size, different hole size, changing a component, changing the geometry of a component. All that stuff can change this design system FMECA to work as a mitigation. A mitigation here is anything that lowers down any of these numbers, while the mitigation on the safety is a mitigation that doesn't cause some other problems. And so that's why we have a tier list on there of the different mitigations that you want to select from that are better than others. So let's go ahead and talk briefly about, we'll spend 30 minutes going over this and going over some examples, or 30 minutes or less, going over some examples and look at the ranking. And then we'll talk a little bit further about this whole thing. So again, FMECA is a failure modes. So FM, failure modes, effects, E. C is criticality, and A is analysis. That's the FMECA, and this is the design slash system. So this is basically a way, and this one and the safety FMECA, you may hear me call them scorecards. Generally, anything with like a number is they call a scorecard. So scorecards are very crucial. They are basically the analysis of your system and ways to improve it. And also, they can easily predict kind of where you are currently and the design process, right? And they're useful in a whole bunch of other ways. That's why we use scorecards and a whole bunch of stuff in our daily lives. Anyways, so this is for the general system. So this would be basically here we're analyzing things that could impact system uptime or damaging the system or other basically critical system failure, other things like that that could affect the customer as far as the functionality of the system and also longevity and the time it would take to repair these other things. So that's mainly what we're analyzing here. And the only safety, this could overlap with the safety FMECA if you have system damage or system downtime. I've split it a little differently than I've seen in other places where the safety FMECA only handles the possible personnel impact, while this will handle possible system impact. So basically, component loss or system loss, or it could just be the system is down, right? And you just lose productivity. So that's mainly what we're analyzing here. And again, same thing in the system safety FMECA. I didn't mention it, but these requirements are just guidelines. You can make it even more stringent than this if you want. These are just guidelines. So basically, this is the requirement SOD, which is severity times occurrence times detectability, is equal to SOD. SOD is just the first three letters of each. S for severity, O for occurrence, D for detectability. So this is basically these three columns multiplied by each other, and that equals this fourth column. And you can see here, I already have the math done in here. And if this column turns red, I'm in the wrong account again. If this column turns red, then that means you need a mitigation. Oops. Looks like this one I screwed up on. This one I didn't. Okay, so let me fix that. So basically, it will turn red, and you do that by format, conditional formatting, and then this should be value is greater than or equal to 4. There we go. So if it's red, you need a mitigation. So this is, if this is more than 100, so let's make it more than 100. So here you see, if you have any red in each row, you need to come up with a mitigation. Okay, so yeah, basically we have components, possible failure modes, potential cause of failure mode, effective failure mode, controls. So there's different ways that you can group this up. I didn't show this here, but I can show you a couple ways of doing that. So one, let's go ahead and jump to the examples and we can talk about this here. So we can have kind of a setup here that I didn't show, which is you can go here and merge the columns together, and then you can have multiple failure modes for each component. So let's say you have, let's say heater here, and then you have like part number, manufacturer part number, something, right? And then this would be multiple things, so you can have like heater here, same thing as above, and then you have, you know, uh, temperature set point, short, oopsies, and then here you can have like short life time, right? So this is how you would generally want to do it. So go ahead and merge together multiple cells so that you can have it be one part number, or one part have multiple impacts, right? So that way you make it cleaner instead of keep having to write heater over again. Just merge the cells. So that makes it way simpler, or you know, that will also help keep things very clean and to understand kind of the failure, all the different failure modes. So let me go ahead and get into this the same that I did with the safety FMECA. So this is the same deal. This scorecard is um, only as good as your imagination or your team's imagination can be. So you want to be as in depth and as honest and as real with this as possible, because you don't want to have problems with this come up later, and then you're basically you look like a tool to the customer. Customer gets it, doesn't work, and then now you got big problems, right? So I talked about this in my analysis with like the Micronics video, the Micronics analysis of their Micron printer, right? They sent out 5 units, one of them didn't work. It completely killed their Kickstarter, I would say. I mean, obviously their Kickstarter did very well, but it basically stopped. So um, take this very seriously. And again, your limitation is only as good as your imagination. Obviously, these ones, and the same thing as the safety FMECA, you want to keep these updated, right? So when something happens, add it here. So let's say you have a failure that you didn't come up with. For example, on the Micronics, it is like their powder getting jammed in the auger. Okay, so you put that on here. What is the possible failure modes? This, and then what's your mitigation? Blah blah, all this stuff. So make sure this guy keeps up to date. And this is not like a one-time. Okay, I spent 3 hours and you're done. You're doing this continuously throughout your development process, or you can have one person dedicated to do this the entire time for all your products. So that is basically the best way of doing it, because you want to be as imaginative on this, because you can actually catch things before they happen and before they get to your customer, improve it. Customer never knew it even happened. You end up with a better product. The better this document is, the better product you are going to have. Same thing with the FMECA. The better the safety FMECA. The better the safety FMECA is, the safer your product is, and thus the better your product is. Compare to your competitors. Same thing here. This is also your competitive advantage, is how good your how good your system FMECA is. Same thing as your safety FMECA. Okay, let's go over this. So these are also inspired by some of my own problems and the mitigations to fix those problems. So I will keep over time adding to this, and you see here notes are basically inside these quotations here. So here again, heater part number, manufacturing part number, something to identify it. So let's say here possible failure mode is it's not meeting temperature set point, and this is impacting your system performance. So you try to turn on your system, and the system is not meeting the set point that you want. So let's say you don't have quite amount of power, or it's very, very picky on how you install it, and the materials causes some weird things, or in different processes you do it, it won't go to the temperature that you want. So now, like, what are you going to do? So these are good points to look at, right? So, and again, there's multiple things that we can do here. Like I showed, heater, heater short life, all these things. So I will try to add something like that where I have these grouped together. So here, for example, potential cause of failure modes. This again happened in real life. Loose contact, loose surface contact, thermal contact with surface. Eventually, over time, because the screws are loosening from thermal cycling, right? And again, here you want to be as descriptive as possible so somebody looks at it later, they can understand your thought process. So, what are the effects of this failure mode? At the max power of the heater, you still cannot meet the set point. Set point again is what you require for the machine: 90, 100C, 200, 120C, 200C, 1000C, whatever, right? So, what is my current controls? So, what am I doing to again, also, this was potential cause of failure mode was loose contact. So controls are, what am I doing to make sure that this does not happen, to minimize the occurrence and the severity. So basically, um, procedure to make sure they don't loosen. I add a lock washer, and this is something that we did on our on one of the this projects I worked on, and it still loosened. Right? Thought that was good enough. Didn't fix it. Severity still high. This causes system downtime. And then you have to do repairs, and stuff's hot, so you have to wait for it to to cool down. You got to be careful, otherwise you have you can get personnel burns, or they are get uncomfortable, or it causes skin irritation or whatever when they're touching hot surfaces. Accidents can happen, things like that. So again, big deal to have something come down and then have to fix it, especially with thermal, because thermal stays there for a long time. Right, thermal will stay depending on the temperature and depending on how well insulated it could stay hot, and also the mass. It can stay hot for a really long time until it drops down to the safety threshold. Right. So here the severity. Let's go ahead and go jump into the rankings. So here's the rankings: severity, occurrence, detectability. This guy like that. Okay. So this is a mistake there. There we go. So here we go. Severity. Basically, and this is a variable. So you can either do 1, 5, and 10, or you can do variation of kind of a 0, 1 to 10. So basically, failure does not stop system and no loss of system functionality, or failure is nearly no downtime for repair. So obviously, this means that the failure does cause something to happen. Otherwise, there's not really a point to have it on the sheet. Number 5, failure leads to temporary stop of tool, short downtime for repair. Number 10, safety issue resulting of failure leads to non-operational system. So obviously safety issues in 10, and then also needs to be on your safety FMECA. Leads to non-operational system, destruction of the system assembly or components. Destruction leads to long downtime for repair. Right. So here's an example: parts being no longer functional, fire, permanent deformation of parts, return of system to manufacturer for fixing. So here's an example for 5, which is a temporary stop, changing a fuse, changing a hard to get to component, servicing a hard to get to component. Right. Um, So a failure does not stop system and no loss of system functionality, or failure is nearly no downtime for repair. Re-enabling a breaker, acknowledging, wow, spelling's really bad here. Acknowledging a warning in the software, lubricating an easy to get component. So this is like just a simple something tripping. So for example, let's say you have a thermal breaker, you have to set it back, um, or you have some warning in the software that won't let you continue until you acknowledge. So some of those, if you're not caught, you're in some sort of automatic mode. It could cause some system downtime, right? Depending on how on top of it the customer is, etc. Occurrence. So this is the S, and then this is the O. So let's start at the bottom. Failure not observed much at all or can't be pinned down as a minor cause. Failure rate below 1%. Pretty much the failure issue is random. So um, basically, it can't be pinned down as main cause, so it could have been something else. We can't really tell what's going on. Again, obviously, in order to know that it is random, you have to investigate. It's the only way you can find out it's random. You don't just say, hey, it's random, and then walk away from it. You need to fix all problems. Remember that. Potential risks that failure can happen. Mitigation of this failure or BKMs not that effective but are in place. Failure rate between 1 to 3%. So basically, you create a mitigation. So this is kind of like what I talked about with the screws, with the washers. I create a mitigation, but it didn't really help. So every once in a while, a component underperforming compared to spec, occasional small or large system stops. So ranking 10, failure of this component is common. Mitigation of this failure or BKM is not yet determined. Basically, we have no idea how to stop it from happening. And we don't have any BKMs or best known methods. So we don't have any best known methods yet to stop it from happening. Many of the components underperforming compared to spec, multiple small or large system stops. Detectability. Number one, failure will definitely be detected during operation and or by existing control methods. So this is the only one that's kind of backwards. So well, same thing here. The occurrence, the smaller the number, the better. Detectability, the smaller the number, the better. Basically, same for all of them. But yeah, so failure will definitely be detected during operation and or by existing control methods. System sensor initial quality assurance or even just clear visual from user can see the failure happening, thus further loss prevented. So it's like, hey, I can see the system is like jumping around or hopping or binding up or making weird noises or anything like that. Or same thing with a car, like, hey, when I turn the steering wheel, the car's not turning. Like the wheels aren't turning. So, or when I get on the gas, nothing happens. Engine doesn't rev up. Visual, easy to tell, right? So you can easily tell, hey, my engine's not revving. That's a failure. Now, what exactly causes that failure? That's a different story. But hey, this is what's happening. Okay, this is how I can talk to the. Also, another thing with detectability is how easily can somebody translate this to the service team if you have a remote product. How easy is it to say, hey, this is exactly what's happening according to the procedure. Here you go. And then you can easily communicate. So obviously, the better that is, the better situation you have. So here with existing control methods, there might be a risk that the failure will not be detected. Problems arising are sort of noticeable, but can't be determined to be exactly as failure as the culprit. So you have your car, let's say similar was on a vacation here recently. So driving down the road, car's bouncing. Okay, is it something wrong with the suspension? Or is it just my wheels aren't balanced? Not exactly sure. So that's not, or is it the road? So there, okay, can't really tell what's going on. So detectability would be like a 5 there. And again, this you can set 1, 5, and 10, or you can set it to be more granular, 1 through 10. Failure cannot be detected during operation and or by existing control methods. Failure is not caught by system sensors initial QA and consumable loss or component loss. Further damage as a result. So basically, you don't even know what's happening. System doesn't know what's happening, but it's destroying itself at the same time, or something like that. Then that you would have a 10 there. Okay, so let's go back to examples. Let's go through examples. So here, heater part number, manufacturer, and this one manufacturer part number. So then we go and basically, so severity, I put 8. I mean, this is basically system down. And now you have to take all this stuff apart. And there's mitigations like talking about in the safety for this heater to keep it safe. So, but to keep it safe, there's more things you have to remove: tooled interlock covers, other shielding, things like that to prevent fires. So you got to remove all that stuff and make sure you document all the screws you're taking out, follow the procedure, do all this stuff. It's a big deal, especially if it's not just your service department, especially if the customer is servicing it or their service team is servicing it. Okay, they have to read all the procedures. Maybe they're not familiar, all this stuff, right? Occurrence is a 10. So like the reason why the occurrence is 10 is that it basically happens eventually. eventually means guaranteed, right? Detectability, kind of hard to tell why the heater isn't stopped functioning. Is it because the heater is defective? Is it because my wiring came loose? Is it because my heater driver has a problem? Is it because my software is not sending the right set point? Is it some sort of loose connection somewhere? Is it because the breaker is off? I mean, maybe, who knows? Maybe the breaker is just off, and that's why it's not getting any power, or something like that, right? So altogether, 8 times 10 times 6 is 480, right? So here's a mitigation plan. Use bevel washers to keep constant lock force on screws. So no longer loosen. This is why the occurrence is low. And then again, inside this quotations is the notes. No longer loosen, and this is why the occurrence is low and severity low. So now this is PM SEV, PM OCC, PM DET, PM SOD. So this is post mitigation severity, post mitigation occurrence, post mitigation detectability, and post mitigation SOD, which is severity times occurrence times detectability. So we have red here. So again, this is above 4, this is above 100. So we need mitigation. This is our mitigation, and now both are green, right? So this will keep that clamped down, so it should be able to meet that setup. So another thing that we could have here would be what would happen. Can we detect if the heater is defective? I mean, at least every component should have a way of detecting if it is defective, right? So this would have another one here. So I'd insert one row above, and then I would have here heater defective, right? What is the possible cause? It burns too long, whatever. And again, most of these things that are in here and inside the safety FMECA are assuming that it is within the service interval. So if you're going way beyond the service interval, same thing like your motor on your car, you're running your motor on your car, and also everything is in standard working order. I'm not saying the same thing like running your car with no oil and it catches on fire. Well, or it seizes up on the freeway and pole vaults the car or whatever, or causes an accident, right? Obviously, the systems that you had in place were not followed. Same thing as if you have the interval is completely disregarded and they're going way past the service interval, parts wear out, causes failure, right? Or causes a safety problem. Okay, that is definitely something. Obviously, you have to make sure the customer does not do that as much as possible, miss the safety interval, but you get the idea. So here you go, heater defective, and then what's the potential cause, all the different things that could happen. The effects is that you can't meet your temperature set point, and thus you can't bring the system online, right? Or you can't run the system. The severity would be a 10, currents very low. Again, this is from testing. And again, a lot of this is from empirical, what you hear back from the field. Obviously, you're going to do as much as you can up front to catch it before it gets to the field, but a lot of this is going to be from the field, and you have mitigation after phase 7 when you are in this one, full release product, right? So this is kind of what it would look like here. So there you go. There's a fix, and I've dropped the SOD from 480 down to 24. So that's 20 times lower score, which is great. Next one, stepper motor. So let's say we have a problem of stepper motor overheating. Had this problem on a printer in the past. Let's say fans not adequate enough cooling, or here, let's say stepper motor overheating, fans fails, so not enough adequate cooling, or stepper motor voltage set too high, thus too hot, whatever, right? So in this case, potential causes of failure modes, the fans fail, so not enough adequate cooling. Effects of failure mode, system movement failure, right? So now the machine doesn't move, and thus it can't perform its action. Severity really depends on the system. In this case, I'm using this kind of as like a 3D printer. So obviously, if the 3D printer can't move, it can't do anything. So that's a severity of 10. System QA. So okay, test it first in your lab. Again, you're running marathons. You should be able to catch this, right? Run your heater in the max. Again, also generally in your specifications, you have like an environment that you have the machine in. Generally, the normal environment 0 to 50C is pretty standard. So okay, you put it in an environment inside an oven that's set to 50C and it runs. Does it run? Yes. Can you run a marathon with it? Does it continue running? Yes. Okay, most likely no problem. Can you repeat it? Can you do it with a big enough sample size that is similar to the sample size that your customer base? Okay. Can you prove that it won't happen at your customer side? Okay, yes, right. So that would be the system Q&A. Temperature sensor on stepper throws error on system when past minimum value. So, and generally the minimum value is going to be, okay, well, I rated the system from 0 to 50C, and most likely the environment has gone past 50C, and I'm monitoring the environment, and the environment has indeed gone past 50C. So what's going on? My fan is also stopped. It seems like it's no longer blowing, right? So it just throws an error, but the system's down. So it didn't really fix anything. That mitigation, right? Okay, it throws error. Hey, fan's not working. Please check into it. System is down. Currents, very low. Fan failing, right? This is maybe even like a 2. Um, Detectability, kind of hard to tell. Is it just because something else in there is very hot? Or again, like I said, is the voltage set too high? Is there some sort of other component failure that is causing this to happen? Is something binding up that causing the stepper motor to skip? What's going on, right? So this is going to be pretty hard to figure out. I think the detectability here is a little on the conservative side. It's probably higher, 5, 6. Can't really tell what's going on. So number one, select more dependable fans. That's one, right? Higher. Another one here is higher temperature insulation steppers. So you have different inductor insulation on the ductor wires. You can get one with a higher insulation number so that it can go higher temperature. So even if the fans fail, it keeps going. But it may have a reduced life, but you can run it temporarily until you get the fans fixed. Add sensor that can detect when fan stops operating, and then add. This is a key thing. Number one thing in system design, system FMECA, and critical system infrastructure, redundancy, more than one. So same thing with the 737 Max. They had this angle of attack sensor, only had one. When the angle of attack sensor failed, it caused people to die, right? Same thing as a lot of critical disasters are from lack of redundancy, or the redundancy is not enough that multiple fail one after another, right? So yeah, key is redundancy when you have key systems. So in this case, cooling can affect your step motors, could affect your system brain, your controller, all those different things, or even the surface too hot. So now you have possible safety concerns, all these things. So add a second fan for redundancy. First one fails, second one's still going. Again, unless it's like some sort of power supply, then both of them die, right? But fault happens after one fan stops working. Hey, I'm not dropping any amperage to this wire. It should be attached to a fan. The fan should be running. Okay, so warn the user, hey, fan's not running. Second fan is running. Please fix the fan as soon as possible, right? And then, so the second one can make sure that the system stays up while repairs are organized. So that's an example of this one, and then I reevaluated post mitigation SOV, post mitigation occurrence, post mitigation detectability, post mitigation SOD. Right. So here I was saying chances of a fan dying very low, 2. It's very because right here 2 also is I completely got rid of it by putting in higher temperature insulation steppers. There you go. Basically, completely got rid of. Okay, both fans can die and stepper motor's not going to go down. There you go. Fixed it. I designed it out. I designed the problem out, right? Of course, you could have a faulty stepper motor. That would be another thing here. So be another one here, right? Stepper motor faulty. What do you do? So yeah, 2 1 1 2. So this is basically what 75 times reduction. Huge, right? So there you go. Just right this one mitigation right here, thinking about it for a brief time, allowed me to build a significantly more robust system. But that's only because I know about these high temperature insulation steppers, which is the key part here, right? Just be able to basically get rid of the problem altogether. So, anyways, that's kind of how you do the design system FMECA and how you help build yourself a better product. Let me know any questions, and I will see you guys in the next one. Thanks for watching. Later.